Another energy conversion process is how we convert thermal energy into electrical and electrical energy into thermal energy. Thermocouple is one example of how to do that. This is another potentially big alternative energy source. Geothermal energy, thermal energy at the bottom, deep in the Earth's crust, or deeper in the Earth's crust, is a source of, you can run water, a couple ways to do it. You can run water down deep and it's hotter, and as it comes up it's going to get heated up quite a bit down there, and it comes up, you've got very hot water. And so you're pulling up that hot water and you can use it to run steam generators, for example. You can run wire from a hot area to a cold area, a thermocouple, and that temperature difference can produce a voltage difference, which you can use to run things. Let me just tell you a little bit about that. For a conductor, if I heat up one side, maybe cool the other side. For a conductor, all the electrons are just this diffuse cloud. They're sort of attached to their atoms, but they move around very well, which is why they're conductors, electrical and thermal. So what's going to happen on the hot side is the electrons are going to have more energy, and they're going to be jiggling more and pushing each other away more, and they'll be spread out. Just like anything expands when it heats up. Now the substrate, the nuclei, they can't move, but the electrons can. And so the electrons will tend to spread out where it's hot. And on the cool side, they won't be moving as much, and so they won't be pushing as hard, and so more of them will collect there. And all of a sudden, just by having a temperature difference, you've created a lack of electrons here and a lot of electrons here. Positive charge here, negative charge here. So a temperature difference produces a voltage difference. But I could do the same thing by putting a very strong negative charge here and a very strong positive charge, very strong positive charge here and a very strong negative charge here. The positive charge would draw all the electrons over and it would cool the side down because they'd be stuck. They'd have to get rid of their energy. They'd give it over here. The negative charge would have fewer electrons there, and they'd be able to bounce more, and they'd get hotter. And so I can take a voltage difference and I can create a temperature difference. Let's see. We use a temperature difference to produce a voltage difference when we measure things with a thermocouple using two dissimilar metals so that there's a junction. They don't spread out the charge the same way. We can create a voltage difference using a temperature difference. For example, radioisotopes for space travel. The Voyager, Pioneer, and Cassini, and Galileo spacecraft, they all used radioactive substances. And the radioactive substances generate heat. And outside in space it's cold. You got this temperature difference. That temperature difference is used to power these spacecraft. It produces the voltage. Voyager left over 30 years ago. It's over 100 times further away from the sun than the Earth is right now, and we're still receiving information from it. But geothermal energy is another way to go on this. Let's see, but that's a little bit different. Okay, so one main way to use this is with the thermoelectric, or TE module. And these tend to be smaller volumes, and they work off of something called a Peltier effect, which is, in essence, something like this. It uses a semiconductor, and the temperature difference produces a current flow. And that current flow removes heat from one system and adds it to another system. So if I had two cups with the Peltier effect and I ran a charge against them, one cup of fluid would cool down and the other would heat up. So let me just do a simple electrical to thermal conversion problem. Say I've got this container, a little bit bigger. These TE modules are the same things where you have these little cups you can stick your beer in when you're driving. Yeah, you can stick your Coke in when you're driving. No, you can stick your Pepsi, your soft drink in when you're driving. You stick it in there and you can plug the cord into the cigarette lighter, the power source, and you can actually cool down the drink. So let's say I've got this container here, but I've just put water in it. And I put electrical power into it. I'm going to put in, let's see, I'm going to put in 60 volts. And I'm going to put in a current of 1.5 amps. And the efficiency is going to be, let's say it's 50%. And the volume of fluid I have here is, let's see, it's 20 milliliters, so it's 30. Let's see, a liter would be way too much for a soda. Half a liter would be a bit much. A quarter of a liter, 250 milliliters. About a pint. No, about a cup of fluid. And I'm going to heat it for, let's see, no, I'm going to find out how long. I'm going to heat it from an initial temperature of 20 degrees Celsius, room temperature. I'm going to boil it, I guess. I'll heat it up. Now let's cool it down. Never mind. I'm going to cool it down. I'm going to take it from an initial temperature of 20 degrees Celsius, and I'm going to cool it down to a final temperature of 4 degrees Celsius. And I want to know how long is that going to take. And let's just say it's water. So I'm cooling water. I could heat it, I could cool it. So A, what's the input power? Well, the input power is the voltage times the current, which is 60 volts times 1.5 amps, which is going to be 90 watts. A volt's a joule per coulomb, an amp's a coulomb per second. Coulombs cancel, I get joules per second. It's a watt. B, what's the heat transfer rate out, which is just the output power. Maybe I should just say output. Well, let's see. The output power is the input power times the efficiency over 100%. I just reworked that equation, which is going to be 90 watts times 50% over 100%, which is going to be 45 watts. C. How long does it take to do that? Well, let's see. The output power is just the heat transfer rate, which is the heat over time. So I can solve for the time. I can say the time, let's see, multiply both sides by time, divide both sides by the output power. The time is the heat emitted over the output power. Now, heat emitted is mass. Heat is mass times specific heat times temperature difference. So that's mass times specific heat times temperature difference over the output power. Now we're going to have to solve for that. We've got to get the mass. We don't have it. So let me do that. The mass is equal to the mass density times the volume, which is 1 gram per milliliter. That's the density of water times 250 milliliters. Milliliters cancel. That's equal to 250 grams. The temperature difference, which I also don't have, is the initial temperature minus the final temperature, which is 20 degrees Celsius minus 4 degrees Celsius, which is 16 Celsius degrees. And now I think I've got everything I need. I've got 250 grams times 1 calorie per gram per Celsius degree times 16 Celsius degrees divided by the output power, which is 45, I'm not going to say watts, I'm going to say joules per second. Okay, so I got rid of my grams, my Celsius degrees cancel. I'm looking for a time. 1 over seconds is seconds, but I got 2 units of energy. I got joules here and calories here. I got to get rid of these things. So let's see, there are 4.184, 4.184 joules in a calorie. Will that work? Joules will cancel, calories will cancel, I'll get seconds. Woohoo! So let's see what we get. Should be about like 38, I think. 39. Whoa, I was off by a factor of 10. It's 372 seconds.